Right, welcome to the online causal inference seminar. Today, we are very excited to have Niklas Pfister from the University of Copenhagen, who will talk about statistical testing under distributional shifts. If you have any questions, please put them in Q&A. Today, we have Nikolai and Sorawit who are happy to answer your questions. As discussant today, we have Thomas Berrett, and after that, we'll take some more questions. Questions today will be handled by Michael, so I'm quickly switching over to him.
Thanks, Dominic. So yeah, we have two people, Nikolai and Sorawit, helping with Q&A today. So submit your questions through the Q&A box, not the chat box. And we may, Niklas is going to pause, so we may ask whether you'd like to ask your question live, in which case I'll ask you to raise your hand and then unmute you when the time comes. Just keep in mind that the seminar is being recorded if you choose to ask your question live. So with that, we'll switch over to Niklas. Feel free to start whenever you're ready.
Thanks for the invite. So let me first share my slides. Good. So I hope everyone can see everything. And
yes, that's good.
Yeah, otherwise interrupt me. Good. So thanks to the organizers for having me at this I think very nice online seminar. So today I'll be talking about, this is a very new work. So we just put a paper of this up on arXiv, and so it would be statistical testing under distributional shifts. And it would be great to hear any type of feedback that you might have on any of this. So this is very new, and so any ideas or something would be strongly appreciated. So this is a joint work with Nikolai and Sorawit, who are two PhD students at Copenhagen University here, and they're also kind enough to be in the panel today, so they will be answering any of the questions that you have put in the Q&A. And it's also joint work with Jonas, who is a professor also here at KU. So thanks to those people. Good. So just to give you a short overview of how I will structure this talk. So the motivation of this work here kind of came from an application that we did with respect to reinforcement learning. So this contextual bandits. But I will not start with this motivation. Instead, I will start with kind of a very abstract general framework, and then kind of give three examples of where this potentially might be a useful concept to have. And one of them I will focus on a little bit more, which will be this contextual bandit application. And the other two will be kind of causality and conditional independence related. After that, then I will introduce kind of the method that we propose in order for solving this original task. So this first part will be just kind of the method and so on. And then we'll see if we have enough time for looking at some of the applications related to the original applications. Good. So let's start with statistical testing under distributional shifts. So statistical testing, I like to always think about kind of having a set of distributions. So this would be your kind of your statistical model, if you like. So this is this calligraphic P, some type of distributions living on some space Z. And then within this space, we have our null hypothesis, which is just kind of a subset of distributions within there. And then generally we have data which comes from some observational, comes from some distribution that lies within there. Think about IID data from the setting. And now I want to generalize this a little bit in the sense that we assume that we do not observe actual data from the setting we're interested in, but rather we observe data corresponding to some other model class Q, which lives on a potentially different space, and where we now have observations, so NIID observations from some distribution that we say here shortly to be Q star. And now, in order for this to be interesting, so we'd like to have this data that comes from a different distribution, and we want to test the hypothesis in this target domain. we need to kind of make some assumption about how these things are connected. And this is what we call kind of this function tau here, which is basically just a mapping between these two classes of distributions. And we think about kind of here this tau mapping individual, so any type of distribution into our new space. And this immediately, by pulling back my null hypothesis from this space, I get a null hypothesis in my original space. And looking at this, I can then perfectly, as normal, define my task of statistical testing. So I want to perform now a hypothesis test. And so this is this function psi, and I would like to ensure that this kind of satisfies some type of level guarantees, so the classical level guarantee would be that for any distribution that I have in my null hypothesis, which is now this pulled back hypothesis, the mistake of falsely rejecting this, so that my test outputs a reject, should be bounded by this significant level alpha. And this we can think about as basically being a test now also on the target space. If instead of pulling this hypothesis back, we just map our distributions into the setting. And now, so this is just some very abstract concept in some sense that I will now show where this arises, because actually it arises in many places. Good. And the first application I would like to talk about is the one that motivated us to look into this a little bit in more detail. And this is this multi-environment contextual bandit. So what is that? So essentially, it's kind of the setting where we have some covariates X and that are observed, and some unobserved covariates U, and so an action variable and a reward variable. And now the reward, kind of, I have my context that on which I base a policy pi that then produces an action A, and then my action together with my context gives me some rewards. So the sampling scheme here is somehow that I first sample these context variables. And now here, the special thing, and this is why we call this the multi-environment setting, is that kind of the data generating distribution for my context can change across environments. So I'm assuming I see something across different environments, and this only affects, so this is kind of only affecting my observed context. So this is kind of the main assumption that we put into this setting. And then based on my observed context, I select my policy, and then I get my reward. So this is the sequential type of draw of how I get my reward. And the goal, as with normal contextual bandits, is in some sense to optimize, to find the best policy that gives me the highest expected reward. And now, because I'm in this multi-environment setting, one thing that one can look at, because now for each environment, of course, I will get a different expected reward. So one can explicitly look kind of at a robust kind of solution to this, which would be, in this case, kind of this worst case expected reward that we look at. So our goal in this setting is to look at this and try to find a policy that kind of optimizes, in some sense, this worst case expected reward. Good. And now just to put an example behind this, so this is not something we're explicitly looking at, but I think it is always nice to keep something practical in mind when we look at models of this type. So think of a healthcare example where we have, we're treating some disease across different hospitals and different patients. So in this context, in this setting, we have that the context of the health indicators, our reward is basically what is the health outcome of the patient, of an individual patient, and the policy would be kind of some treatment protocol for this disease. And the environment you can think about as being different hospitals. So now I have learned I've observed data on 2 hospitals, and now I want to kind of generalize to different hospitals to a different hospital that I have not yet observed. And some things might change in there. And in particular, we kind of allow now the distribution of kind of the health indicators to shift across environments. So now, is causality a useful framework in this setting? And there is, I think this, so I like to split this up. I don't know if everyone agrees, but so one way of splitting this up is, so the modeling, there's the modeling component, and then there's a learning component. So first, the modeling component. And I think from a modeling component, it is actually quite clear that this could be a good, it could be a useful concept of including causality here. And what I mean by this is that this idea of this environment that we have is very natural to think about in terms of interventions. So you can think about keeping certain parts, so interventions are good at modeling settings where I keep certain parts of my system fixed, but change other parts. So, I mean, this is arguable if this is the best setting, in particular, if you think about this hospital example, but causality really has a nice way of kind of inducing distributional shifts across marginal parts of your distribution while keeping other parts of the distribution fixed. So in this case, I think it is useful. And now there is a second component, I think, to causality, where one can ask now, okay, so now I wrote down my model, this would work very good doing whatever favorite causal model I was using in this case. So we use structural causal models, but you might use something else, and you wrote down your causal model, and the question kind of is, do I really need now this structure of these interventions? Does this somehow benefit me in learning a better policy? And this is, I think, a little bit of a harder question to answer. And what I mean by this is that, does it make sense to go beyond a predictive model? So if I just forget about my environment structure entirely, and I just apply my favorite contextual bandit learning algorithm to optimize my policy, will this policy that I learn work well in a third hospital that I have not observed yet? And if this is the case, then I would argue that you don't really need the causal model. If it's not the case, so if I can really benefit by incorporating this additional structure that I get from my causal model, then I think causality is also helpful in this learning principle. And so what does this look like in the setting? In this setting, I would argue that without hidden confounding, this might not come as a huge surprise. It actually is not necessary to really consider the environment structure at all. And this is a very simple result that we have. So if you now pool together your environments, so we have these observed environments, and this is all of our environments. So this is hospital 1 and 2, and this is now all hospitals. And so now if I just take my first 2 hospitals and I pool them together, I don't care where they came from, I learn an optimal policy, I know there is no hidden confounding, so these U variables do not exist, then I can pool them together. And in the population case, this policy will also be minimax, maxi-min optimal with respect to this larger class of environments, because there cannot be any shifts that I can make use of. So this means kind of that on a population level, I can just pool everything together. Now, what happens with hidden confounding? So here, the setting gets a little bit more delicate, but also more interesting, I would say. And let's look again at this very simple example that I gave here at the beginning. So what can go wrong now if I learn a policy here and some of these marginal distributions change? So one thing that can go wrong is if we look at this x1 here. So this is only confounded here, of course. And now if in one environment, basically, this might be a very good predictor for R. So I can use kind of this confounding structure to give me a good indicator of what policy I should choose. I can, if my intervention somehow is, or my environment shift to a different environment is so adversarial that it kind of flips the dependence of U on X, this can potentially even revert to being like a very harmful policy in a different environment. So this already gives you somehow an intuition that what is going on is that I need somehow a large set of environments, and at the same time I need kind of this hidden confounding. And to make this a little bit more formal, what we do is we define kind of a notion of invariance on policies. So we say that a policy pi that now depends on some set S, so in this case our pi depends on x1 and x2, we say that this is invariant with respect to that set if this mean conditional invariance type holds. So the conditional of R given this set of variable under this policy is remaining fixed. And what you can think about here, if you like thinking about graphs, this is a little bit easier in this case. You can just think about E being conditionally independent given the set that I'm looking at of R. And in this case, of course, if I now include x1 and x2, then this path appears opening up in the graph, which means that I'm not conditionally independent anymore. And let's just look at two examples. If I only have a policy at pi bar, then one of these edges goes away and I'm only conditioning on the set x2. And you immediately see that now this top path is blocked kind of, and I'm kind of in a safe haven. So this will be an invariant policy. And this is just the other example. Good. And now, so what happens if I now have this setting? Can we say something about generalization? And the answer is yes, under certain conditions. And these conditions are, so one of them is just mean faithfulness. So this is just so we can have kind of translate from our d-separations in the graph kind of to the conditional independencies. And then the second assumption, and this is the very important assumption here, I think, is that our environments need to be strong enough in some sense. So that we need to be able to basically flip some of these signs. So it needs to be adversarial. So if you think about very small changes only happening across hospitals, then potentially a non-invariant policy might be beneficial. But if I have some of these additional assumptions, then I can look at a policy that is optimized only over the invariant policies. So now I'm only looking at invariant policies. Then I know that this will be always at least as good or better than a policy that is non-invariant. So this then suggests that if I now am in such a setting, then I would like to optimize over these invariant policies. And this will kind of give me like kind of at least a robust choice across environments. And this now motivates the original setting that we were looking at. So how can we determine whether a policy is really invariant or not? And the problem is that we generally, so if we look at kind of this offline contextual bandit, what we have is data coming from some observational setting here on this left-hand side. So this might be a policy that uses x1 and x2 in some way. But what I would like to test, whether this red policy over here with the bar on top is actually an invariant policy. And I do not have data from this setting. So here, this is very much this natural thing. I kind of want to shift my data into, with this tau, into a new distribution, and then perform my invariance test here. Invariance test, you can think about this just as being testing whether E is conditionally independent of R given x2 in this case. Good. So the solution in this case is statistical testing under distributional shifts. And so how does this work? So just shortly recall again, pi my observed policy, and this red pi is the target policy. Then we can construct kind of a shift basically just by doing a reweighting approach. So if we expand any density of our original model, so this will be some Q that now depends also on E, over my observed variable, which are R, A, X1, X2, then I can factorize this as I did here with my policy and my marginal densities over my observed x's and the conditional of the reward. And I would like to map any such density basically to a new density, which now has here basically this pi replaced by pi hat. So how do I do this? Well, I just multiply it by pi hat over pi. So this is very common in reinforcement learning as kind of this reweighting approach. So this is kind of a shift that now shifts any density that originally was constructed under some policy pi to a new density that is now corresponding to a different policy that I'm interested in. And then under this shifted thing, I do my invariance test. So this is the idea for this setting. Okay, now example 2, which will be now a little bit shorter. So this was our original motivation with this contextual bandit. And now these problems also appear in different settings, I would argue. And so one of these settings is, for example, conditional independence testing. So think about 3 variables, and now we want to test x. It's conditionally independent of y given z. So this is a very well investigated topic. And from a causal point of view, this is, of course, very important also. So you can think about, for example, assuming a causal graph of this form, and you're interested kind of now, you have this confounder here, x, and you think about x as being some treatment and y as being some outcome. Then you might be interested in, is there a causal effect from x to y? Now here I put randomized because sometimes it might be sensible to even think about this conditional as being a known function. So here the causal conditional is now x given z, if I assume this causal structure on here. And for these types of settings, there actually have been developed specifically for this quite powerful tests that assume this knowledge. And so, for example, this conditional randomization test and the conditional permutation test by Candice and Tom, who is a discussant here today. So it's nice. And then one can also look at a setting where this graph structure might be somehow different, so that instead of a confounder, now I have a mediator. And then this conditional, the sensor, the causal conditional kind of that I would assume kind of here to think about is z given x in this case. And now, of course, I have kind of a mediator. So the question is kind of a different one. It's now kind of, is there a direct causal effect from x to y that does not go over this mediating path? So these are settings that I can answer if I have a good conditional independence test. And now I want to kind of remove, again, all these edges that I put in here and just say, let's just look at this and kind of now, just for the sake, without any motivation, why we might have this, but let's just assume we know this conditional z given x. And now the question is, can we test conditional independence, so x conditionally independent of y given z, given that I know this conditional as well? So I just put this in the null hypothesis. You can also think about it as being within your statistical model. So this is our goal. And now we want to use this idea of testing under distributional shifts to maybe translate this into potentially an easier problem. So this comes with a little caveat that I will discuss in a second. But so potentially what we can do is, again, we can say, okay, let's just replace this conditional z given x by some condition, just density over the z variable. So again, I can take any density that I have over my 3 variables here, and I multiply it by this scaling factor. I assume this to be known. And now, if you think about back to this mediating setting, then this is, of course, the natural factorization, the causal factorization that I would do, but essentially you could use any factorization that you like, but we use this particular one because we know z given x, right? So then we immediately get for any q that lies within this null hypothesis, this thing will pop up here and it will cross out with this fraction. So what we get is this phi of z here instead. And now you already see that if I also now assume that my original q lies in this null hypothesis, I also have that x is conditionally independent of y given z. So this means I can cross out this little x here. And then if I now marginalize out over this, my z, then I see that my density in this shifted, so under my distributional shift, my new density tau of q satisfies actually that under this density x and y is independent, so without the conditioning thing. So the conditioning part of conditional independence testing kind of just is hidden now away by us assuming that we kind of know the structure. Okay, so and again, we are kind of now in the setting of testing a hypothesis in a target domain. And now let me just shortly say a little comment here that this is a little bit different than the first thing, because in the first example, we were kind of really interested in testing a hypothesis for a target distribution. Now here we were kind of wanting to test something in the observational domain, which was complex, and we kind of now moved it to something in the target domain, which might be easier. So this is kind of a slight difference to what we did in the contextual bandit. Okay, last example, and this I will only cover very shortly, is this Dormant independence. So here I have two graphs, and I assume now x1 to x4 are observed and h hidden. So this is a very famous example by Verma and Pearl. And so if you have these two graphs and you have a distribution that is Markov with respect to either of these will induce the same conditional independencies. So you cannot distinguish between these two graphs simply by doing a conditional independence test. But what Verma here noticed is that you can actually distinguish by these by what is called the Verma constraint. So the causal structure here is clearly different because I have this direct causal effect, right, from x1 to x4. And this Verma constraint means that if I have a distribution that comes from G here, then there must exist a function f that in particular does not depend on x1 that satisfies this integral equation. If you want to see here on this side, you have dependence on 1, and this actually kind of goes away. And so these extra constraints are something that are plainly in the observational distribution and that one can potentially test for, right? So you have a hypothesis that says kind of, is this true or is it not true? And a simple or maybe easier way of visualizing this particular Verma constraint here in this particular case is thinking about these dormant independencies. And what does this mean? This means like if I intervene on x3, so I shift my distribution by doing a do intervention and removing any incoming edges and replacing this, for example, with the normal distribution, standard normal, then what happens is that x1 and x4 in this interventional distribution will become independent. So x1 and x4 is independent in this interventional distribution. And this is what is called the dormant independence. So this is basically the same constraint in this case. And yes, so this can help. How can now, so how does this connect to what we did? In this case, it's actually quite direct because the Dormant constraint is already basically a hypothesis. So I have this complicated Verma constraint, which corresponds to this Dormant independence test, independence statement, which is basically looking at now a shifted distribution, which means I take any distribution in my original space, I do the do intervention, and then what I get out is a new distribution in this new space, and there I can now test, I would like to test this constraint. And this kind of, if you like, this corresponds to x3 given x2, so replacing this conditional by a different density here. Good, so this is it with the introduction, and now I will shortly go over, which is very short, fortunately, the method of how to actually solve this, but maybe there are some questions that showed up. so far?
Yeah, it looks like we haven't received questions yet, so maybe just go on for now.
Okay, so then I will go on. Thanks. Good. So now we have a kind of a general concept of what a test in the distribution in a target domain means when we observe data in a different domain. Now, how can we generally perform a test on the setting? And this is now what I want to go over. So just recall shortly the setting. I have the observational domain, I have the target domain, and now I have this distributional shift function that is kind of assumed to be known. And it kind of corresponds, as we saw in the settings that I described, kind of to shifting or multiplying my densities. So we're only talking about densities here, multiplying them by some shift factor. And now I call this here RQ because this can potentially, so if this can depend on Q, this can be potentially anything. But there are two settings. So either I know kind of that this does not depend on Q, which was kind of the setting where I knew the conditional, if you think about the conditional independence testing. And if I do not know the conditional independence testing, I can still do it, but then my scaling factor would depend on Q. So these are two settings. And now what is the goal? So we want to test a hypothesis like this in the target domain, and we're given IID data, say n observations in our observation domain. And this is kind of the transformation that we know. And the idea now is to construct a test. And in this case, we will not construct a test with valid level because this might be tricky, but instead we construct kind of a test that has asymptotic guarantees. In this case, this pointwise asymptotic level guarantee down here. And I would like to discuss maybe this in terms of two explicit settings. So one of them is this point where RQ is known. So then it does not depend on Q in particular, and this R function is null. So this was, think about the conditional independence testing where I knew the conditional, or the contextual bandit where I kind of knew my two policies that I was looking at. And the second case is, so what happens if I do not know this one particular? Can I just estimate it from data? We will see that this works under certain additional assumptions. Good, so how does the procedure work? Well, we will do something that is very similar to just resampling. So there's this sampling importance resampling procedure that kind of just resamples data, but so this is slightly different in terms that we still have our weights here, but we only sample distinct sequences. And this is slightly different than sampling without replacement with these weights because it kind of weights this a little bit different. So it's a little bit tricky with this otherwise. So we only sample distinct sequences of size m from our data according to this weight function that we have. So R is known, right? So we have this thing, so we can actually sample from this. And then what we do is we have this resampled data, which is reweighted in some sense to mimic kind of the distribution in the target domain. And in the target domain, we assume that we have some test that performs the hypothesis test in the target domain, and we apply it to basically our resampled data. And this then gives you a procedure. And this procedure actually then can be shown to have exactly this pointwise asymptotic level guarantee that we want without any assumptions basically on the phi m, except that this test in the target domain needs to have pointwise asymptotic level as well. And so then we have these two other assumptions, A1 and A3, that also need to hold. And these, so A2 kind of means that I cannot sample too many data points from my sample. So my full sample size is sample size n. And now my resample, I can draw at most of order. So it needs to kind of grow smaller than square root n, which is a rather strong constraint, you could argue. But as soon as you get larger than this, these guarantees break, and one can actually also see this in practice. And the second assumption here is kind of something that might be familiar to people working with reweighting schemes. And this is kind of that our weights in some sense need to be well behaved. So in this sense, we require bounded second moments across these things. But under these conditions, then we really have that this works without constraints on kind of our test. So this needs no linearity assumptions or anything within the test, which we think is quite nice. Now, how does it work if I do not know this, the R function directly? So then one approach is I kind of split my data into two. I take half of it to estimate my RQ, and then I do my reweighting with my estimated R function, and then apply again the test. So here, what do we think about the setting here? This is kind of, if I think about my this conditional independence example, if I do not know the conditional, I can estimate it from data, right? I could estimate this density if I know some model class. And now if I can somehow put an additional guarantee on that this estimate will work sufficiently good, then actually we end up that nothing much changes. And I get, again, this pointwise asymptotic level guarantee. And so what do I need? I need this assumption A0, which kind of means that this estimate is consistent, and it's consistent with a certain rate that depends on some A, but this can be very, very slow. But as you will see, this rate here kind of pops up again. And this means that, of course, I will pay a price for this estimation, and that is that I can now even lower. So if you think about this as working very badly, my estimate, then I, of course, will only be able to sample very few subsamples that I can draw because of this now updated condition. And A3 is also now, of course, modified to be stronger now, because now we get this Q also in this constraint, again below. Good, and now, yes, 5 minutes left. So I can now go over some of these applications back, and let's see how actually this procedure that I just introduced works on actual data. So let's, again, first look at this contextual bandit setting. So here we have exactly the setup that I had before, and the data is generated with respect to this. Is not very important how explicitly it's done, but you can have a look. And importantly now, what do we do, right? We wanted to do this invariance test, and we do this for different sets of variables. So for every possible subset that we look at, so the empty set 1, 2, and 1, 2, we now resample data according to a policy pi s that only depends on these on this set that we're currently looking at. And then once we resample the data, we then perform an invariance test. And here we just do, as an invariance test, think again about, so now under this new distribution that I got from my resampled data, I want to check whether E is conditionally independent of R given XS. And here we just check whether the mean changes across environments using a t-test. And this works surprisingly well, actually. So what we have here is, so different colors correspond to these 4 different sets that we look at. And on the x-axis, we have our sample size, and on the y-axis, the acceptance rate. So if I have an acceptance rate, a high acceptance rate means my test barely rejects. And if I have a acceptance rate of 0, I always reject. And so now what do we want? So if you think back to our setting, we know exactly that in this specific example, the only invariant set is actually using x2. So also the empty set is not invariant. So all other sets except the 2 set are invariant. So, and x2 is exactly this green set that we see kind of preserves more or less level. And we see kind of that, so at least if I have now more training environments, so here I have 2 environments and here I have 6, we see that in this case, I converge essentially, and this is kind of our theoretical result, right? It converges to the level that we want. And at the same time, as I increase, of course, my sample size, my power also increases, which is nice. So we are able to reject these sets in this case. Good. Now, also the conditional independence. So this is, again, just the toy example that we looked at. So you can put some distribution on X, and we take this graph structure here. So this is now a setting in which we have basically this mediator in between X and Y. And we want to test, like, is there a direct causal effect that is parameterized by theta that goes from X to Y? So we have this term here in the Y structural equation. And now you can think, we looked at two settings. So one where this effect is very simple, so it's a linear effect, and the second setting where this is a quadratic effect. And now what do? We shift our data to basically replace this conditional here by a different thing, which is just the density of a Gaussian random variable, where we set the mean and variance to the empirical marginal of Z in this case. And then we perform, so we resample our data and we perform our test between X and Y. And yeah, so this is what we get. So these two plots here on the right hand side are two conditional, so general purpose conditional independence tests. So we have the kernel conditional independent test and generalized covariance measure. And here these two colors correspond, one to the linear effect and one to the quadratic. So this corresponds exactly to tau being 1 or tau being 2. Okay, and now we see that in the linear case, these measures pick this up very strongly, and also with a very, so on the x-axis, we have strength of the direct effect. So this was this parameter theta, how large this is. So if this is sufficiently large, then all of them pick this up all the time. Now, our methods are, of course, not as good here in this case, but I think they actually perform quite nicely if you think about what they're doing, because I think in this case, we have a sample size of 150 or something. And now, of course, for our test, we can only use the square root of n sample size. And what do we do here? So this derepl is just the type of resampling. So that's not very important. So just think about this as being exactly what we do. And in one case, we do a linear test. So this is this core test. We just test for non-zero correlation in the target domain. And we see that it picks up the effect slower, but it still picks it up for the linear case. And also what is nice is it does not pick it up for the case of a quadratic effect, because in this case, it's set exactly that there is no linear effect in the quadratic setting. And instead of doing a linear test, we can also just combine our method with a non-parametric test. In this case, we use the Hilbert-Schmidt independence criterion. And then we see, again, that we are able to slowly pick this up in somewhat relatable level to how the kernelized test does this. And the nice thing is, so here I was saying, of course, okay, so our method kind of assumes that the conditional exists, which is true, which is a very strong assumption, but one can also kind of drop this a little bit and do, so hsig fit basically estimates the conditional first on the data and then does the test. What we see here kind of is a little bit that it moves, potentially kind of affects also this level guarantee a little bit, that you would need a larger sample size in order for this to work. Good. I will skip the Dormant independence test, but essentially it's kind of the same story. You can apply it again, and the nice thing is that it seems to somehow actually work, which is kind of cool for these very complicated models. Good. So let me just shortly summarize then. So we had the statistical test under distributional shifts. This is kind of construct of thinking about testing under distributional shifts, and we saw that this kind of appears actually in quite a variety of different settings. And we saw that in some sense, it can be interesting both from that we actually want to test in the target domain, but it can also be a useful concept of having a test in the observational space, which is kind of with a complex null hypothesis, and by mapping, potentially, it can be simplified in some way. And I think this has, in particular, this last bit can actually be an interesting area of future research. And then last thing I introduced was this resampling procedure that we saw actually is able to achieve these level guarantees under quite general settings. And of course, this is not an all-purpose like solve everything procedure, but in particular because it has quite these assumptions that you need to reduce kind of your sample size quite large. So it has the biggest caveat, of course, is that you need these large sample size in order for this to work, but seems like it's a nice procedure that can be very simple. So it's a very simple procedure to apply to quite difficult tasks, which we think is nice. Yeah, and then the second thing was this multi-environment contextual bandit, which I should also focus on. And one take-home message there was, without confounding, it seems that predictive models can, in some sense, be optimal. And if we have this confounding setting, then invariance really is maybe a concept that, where the causality more generally can actually benefit even this learning component. And it might make sense to look at these invariance tests under distributional shifts. Good, and that's it. So thank you for listening. Here is the archive number for the statistical tests paper, and our second paper is coming also on archive soon, but without a number so far. Good, thank you. Any questions now?
Thanks, Niklas, for the nice talk. Yeah, I have one quick question. So for the resampling procedure, you only resample with a much smaller sample size, right? So yes. For that, is there a way can you make additional assumptions so that you can resample at a higher sample size, or is there some fundamental limit?
Yes. So this is actually the case. You can get, and this depends a lot on your test, I think, because so if your test is, for example, linear or something, you can basically sample. You can think about reweighting without drawing these distinct sequences, but drawing arbitrary sequences. You can potentially go infinite, and then kind of what the method corresponds to is just importance reweighting, because then if these are individual terms, it's just a linear thing. But if you now have a very complicated test statistic, for example, the variance or something, then these issues start becoming up. And so we see that, actually I have a slide for this. Assumption A2, yeah. So here we have, so on the bottom, we kind of have the rate of the sampler. So it's enough to kind of look at this middle plot, and you kind of see that even if I go a little bit larger, depending for this specific test that we look at, actually we can go larger and we still kind of have these guarantees, but then eventually it will always start breaking, because I mean, it makes sense, right? So if I do distinct resamples and I have the same m equals n, then I'm just taking the entire sample. So it will always break.
Yeah, okay.
At a certain point.
Great, thanks. All right, then let's move on to the discussion. So we'll have Thomas present some slides, and after that, Niklas, you'll have the opportunity to respond.
Yes, so I will stop sharing.
Yeah, Tom, whenever you're ready.
Okay, sorry. Can you see this now? Okay, great, thanks. Well, thanks very much for the invitation to be a discussant here, and congratulations to Niklas and his co-authors. I think this is a really interesting paper, so it's really great to be asked to contribute to this session. So what I'm going to do here is I'm just going to kind of give my perspective on this work and I'll focus probably mainly on the conditional independence testing problem because that's what I'm most familiar with. But I'll also give a kind of brief overview of what Niklas and his co-authors have done here. So to go back to the abstract setting, what we have is we have some distribution Q star from which we have data, but what we're really interested in is this other distribution P star. Now, of course, we need to assume that there's some relationship between these two distributions. If we just had any old two distributions, then of course we couldn't learn anything about one from the other. So we need to assume some relationship. And in this paper, the authors are assuming a specific kind of relationship, which I'll come on to later. So perhaps the main motivating problem here, as Niklas discussed, is some kind of off-policy learning problem. So we may have some policy that's been implemented in one hospital and we have data in one hospital, but we want to know about what will happen if we implement this policy in a second hospital. So we want to transfer knowledge from one setting to another setting, and that's perhaps the main motivation here. I think this is kind of related as well to the fields of transfer learning or domain adaptation. So in many tasks, you can think about having data from a number of different sources, which may be quite heterogeneous. And you may want to combine information from different sources to solve a given task. So for example, Kai and Wei here study a classification problem when you use both data from P star and from Q star. And this seems to be something to me that is relevant to this problem here. A big class of the applications that Niklas has talked about is in using this approach to incorporate knowledge to solve a hard problem. So for example, in conditional independence testing, there's just a single distribution that we're interested in. We're interested in the distribution that generated the data, but we're coming up with a kind of transformation internal to our procedure, which allows us to incorporate knowledge of some of the conditional information. So this kind of setting, this distributional shift, is something that we introduce ourselves to make the problem at hand easier. Just a brief overview of the procedure, because this is going to be relevant to what I'll say in a minute. Of course, the approach that we take in such problems is very heavily tied to the form of the relationship between P star and Q star. This is really going to drive how we solve this problem, and different relationships are going to have very different solutions. Here, we're assuming that the likelihood ratio of P star to Q star is known, or is approximately known. You can also think about estimating this ratio. And if you're assuming that you know what this ratio is, then this naturally leads you to think of approaches that are kind of rooted in importance sampling. So we have this subsampling technique, which kind of traces itself back to Rubin. And we use this technique to draw a subsample of our data such that we may regard this subsample as a sample from P star. In most statistical tasks, when we take a subsample, we would take that uniformly at random from the original sample. But what we're doing differently here is that we're weighting the different subsamples differently. Okay, so we're weighting them according to this ratio P star to Q star, and that favors samples that look more like they came from P star than Q star. So that's how we take a sample from Q star and make it look like a sample from P star. I think one of the great strengths of this approach is its flexibility. So what we're doing is we're taking data from Q star, we're outputting a data set from P star, and then we can basically do what we want with that data. So here we're using that data to solve to test a hypothesis, but in principle, I think we could do anything we wanted, and this I think this is a great strength of this work. And yeah, so we kind of have a black box situation here when any test, however complicated it is, can be used after doing this. This is not something that Niklas explicitly said, but it seems to me that also because of this fact, we could also augment this resample data with additional data from P star if that were available. So I think this is another interesting thing. So going back to the kind of transfer learning setup, you would often try and synthesize two data sets to solve one task, and you could perhaps do something similar here. So I'm going to talk a bit more about conditional independence testing, as I said, so that this is more what I know about. And here, we want to just learn about the data generating mechanism. So we suppose that we have triples x, y, z from some distribution q star, and we would like to test whether x is conditionally independent of y given z. It's now formally known, since Shaw and Peters at least, that this is a hard problem. So I'm not going to go into formally what that means here, but essentially we require additional knowledge or additional assumptions to reliably solve this problem. What this method does is it allows us to incorporate knowledge of one of these conditional distributions in order to solve this problem more reliably than if we didn't have that knowledge. So if we know the distribution of z given x, or x given z, then we could use the techniques that we've discussed so far in the following way. So this ratio here, I hope you can see this. This is the function r, which is like the ratio of p to q. And if we multiply that by q, then we end up with this, which under h0 simplifies like this. So what we're doing is we're separating x and y in a way. So now to test the conditional independence of x and y, we no longer have to worry about z. We can just kind of consider this marginal problem. It's well known that testing independence is much easier than testing conditional independence. And that is, I think, in essence, the idea of this approach. We're reducing this difficult conditional independence testing problem to the simpler problem of independence testing. And this is one nice way of simplifying the conditional independence testing problem. Of course, there are other methods for simplifying the problem, so I'll just give a bit of context here on other methods in the literature. So perhaps one of the most natural things to do when faced with a conditional independence testing problem is to consider regression models. I would say that the most basic conditional independence test there is the t-test in a linear model. And this is, so therefore it's very natural to consider regression models when we're dealing with a conditional independence testing problem. Formally, what we might try and do is regress out the effect of z on x and y, and then test for independence between the residuals. So as in Niklas's method, we're kind of reducing a conditional independence testing problem to an independence testing problem. And this is a different way that you can do it. Another way, which is something I've worked on, is also using knowledge of one of the conditional distributions. So this is the version I worked on was the conditional permutation test, but this was based off something earlier called the conditional randomization test. And what you're doing is you're using knowledge of the marginal to generate critical values. So I want to kind of relate this to the current method. So as I was saying earlier, usually in statistics, when we take a subsample, we would do that uniformly at random, probably in most cases. But the difference with this method is that it's done in a weighted way. So the randomness is non-uniform, and that allows you to have a different output that's more relevant for your problem. And this is a similar kind of idea to what we used in the conditional permutation test. So rather than taking uniformly random permutation tests, rather than taking uniformly random permutations, which is what you would normally do, we take weighted permutations. So permutations where the random distribution is not uniform. and thus we can kind of deal with conditioning. So that's one kind of parallel between this work and our work. Okay, so I'll just finish off with some questions. This has already been asked, but I think it's quite a natural question, is how large can we take M to be? Of course, in some ways, M here is kind of equivalent to power, right? You want to take as large a subsample as you can to have more power. So it's quite natural to wonder whether this is necessary, this condition of having M be little over square root n. The next point is, again, something that was raised in the paper. It's quite natural to think about going from pointwise asymptotic guarantees to more uniform guarantees. Perhaps this would involve restricting to certain more amenable H0. So it may be that for independence testing or two-sample testing, for example, you can more easily give uniform guarantees. I wondered if, so this third question, I didn't see any mention of how close P star and Q star were. And it seemed to me possible that if your distributions are very close together, then maybe the problem would be easier. I don't know if that makes sense, but it may be that you can choose M larger if you have stronger assumptions on how close these distributions are. Going back to conditional independence testing then, one nice feature of the current method is that you can use Q star of X given Z, or Z given X, or you could use Y instead. It's very flexible. I wondered if there was a way maybe to incorporate more knowledge, so knowledge on both X and Y. And then finally, a very general question. So can we do anything beyond hypothesis testing? So as I was saying earlier, I think this is a very nice flexible method in that you just get a data set as output. So in principle, you could do anything with that data set afterwards. I wondered what would the challenges be if you wanted to do something that wasn't hypothesis testing? Say, for example, if you wanted to do something that was an estimation problem. And I just have some references here, but otherwise I'll leave it on the questions and I'll pass back to Niklas.
Hi, thanks. That was very nice. I think a very good summary, actually, maybe even better. Became clearer than what I saw. So now the questions are gone. If you can put them maybe up again. Then, but so I have some, I still remember one of them at least. So a very good question. So the first one we answered, right? So it's not so necessary, it would depend on the thing. So I have the feeling, this is not shown, of course, that you can probably come up with tests where this is really necessary in some sense. But depending on how simple and nice your distribution is, then the easier it comes. And now this also goes to question 3 here, I think. Relates in some sense, and this is true. So we hide kind of this P star closeness to Q star is hidden in this in our last assumption, where we kind of say that our weights, kind of the square root of our weights is bound, so the second moment is bounded. This is kind of very close related to this, and this bound will be better, and the finite, so the closer you are, the better your finite sample guarantees. So the better your finite sample performance will be, in the less you need to, also the larger probably you can choose your M in finite sample in particular. So this is it's a good point, and I think it would be nice actually working this out a little bit. Regarding this second topic, actually there has been a little bit of progress. I should pray not to, but I think we actually have, so I think it's possible to get to uniform control. Given that we, of course, put then also some uniform assumptions on these boundedness of these weights. And yeah, we still need to look a little bit into whether these, so if you now look at this in a uniform sense, I think then the question becomes kind of, okay, so now we have this assumption, now we get uniform, but is this really a sensible assumption or something that can be satisfied? But I think you can, and this probably also goes, the harder your testing problem is, the harder this weight thing, or so the larger your shift kind of in distributions will be, the harder, the larger these bounds on these weights will be. So this is kind of, it all kind of interplays a little bit together, I think. Yeah, the fourth, this is a good thing. So I haven't thought about this. I think that's a very nice idea, actually, incorporating. So we only so far ever tried incorporating one, but it would be nice if one can get even more like information that is available into the setting. I think it's very nice. And beyond hypothesis testing, also a very good question. And I think it's actually not so much looking into, so it just came. So why did we look at hypothesis testing was because this contextual bandit thing we looked at, but I think you can also use similar ideas for testing in general. So here we look, our results now currently are all just asymptotic level, right? Because this is what we generally want for, or the most important thing for testing. But essentially you can get this type of convergence then also for estimators, yeah. But thank you, thanks a lot, Tom, also for being here. It's nice.
All right, thank you so much, everyone. I think it's time that we wrap up. First, thank you so much, Niklas, for a very nice talk. Yeah, thank you also, Nikolai and Soravit, for helping out in Q&A, and thank you, Thomas, for a very interesting discussion. Quickly about next time. Next time we're going to have Leon Botou from Facebook. Thank you all for coming. Hope you have a great week, and see you next time. Thanks.
Hi.